In today's video, we're going to be going over section 11.1. And if you'll remember in chapter 10, we were dealing with a situation in which we had a population. We were hoping it was a normal population. Then our sample size wouldn't matter. But we had a certain population mean and a standard deviation. And our assumption was that this was known, the standard deviation was known, but we didn't know the population standard deviation. So we would take samples and we would create X bars. And because we knew this population standard deviation and our sample size was large enough, we could come up with confidence intervals in which we would utilize this formula. So this was known, therefore we would look up, if we wanted to say a 95% confidence interval, to estimate what this population mean was. We would use Z star values that were corresponding with the level of confidence we wanted. Now we're going to do much the same thing in this chapter, except this time we're going to say we don't know that population standard deviation. So we'll have to let our sample standard deviation be used as our estimate for this, and that's going to cause us to have to use a different distribution, and we're going to have to use something called a t-distribution. So let's just go down to the example to begin with, and then we'll go back and look at the formulas that I have up above. So we have in number 10, this again comes right from the book, we have a researcher did some blood tests on several dialysis patients on 6 consecutive clinical visits. One variable she measured was the level of phosphate in the blood. An individual's phosphate level tends to vary normally over time. So we know that if I were, again, looking at this little picture, we're saying that this population of all the different phosphate levels in your blood would have variability, and that you wouldn't always have the same phosphate level. That would change over time. There's a certain standard deviation that would be associated with it, and a certain mean for an individual patient. And so we have that the data for one patient in milligrams of phosphate per deciliter of blood are as follows. So these were 6 different measurements on one specific person. And so we want to calculate what the sample mean would be. So we just want to find this, add them all up, divide by how many there are. And then we want to calculate the standard error. Now the standard error is going to be the standard deviation of sample means. And it's going to be that standard deviation of an individual sample divided by the square root of n. So this would be the standard deviation of how individuals vary divided by the square root of the sample size. And remember, the context is if I had some population and there is a certain mean and there is a certain standard deviation associated with these values, I take samples of size n, and if the original population is not normal, then we want these to be relatively large, so the central limit theorem kicks in, and we get an X bar, and then we take another sample size of 1 and we get another X bar, and so on. And how these things vary are the standard deviation over the square root of n. Now our only problem is we're not going to be knowing what that value is. It is a value, but we just don't know what it is. And we don't know what that is either. So both these are unknown to us. And that's what's being stated up here. So these X bars are going to vary, we know. And in Chapter 10, we knew what this standard deviation was. Now what we're going to have to do is utilize this sample that came from n numbers and look at all these little individual scores, all n scores that were used, and we're going to have to calculate the standard deviation of those individual scores. And we're hoping that this S value is very close to this standard deviation. Now, we're not silly enough to think that every time you collect a sample that your standard deviation from your sample is going to be the same as the standard deviation of the population. But we're hoping that these are quite close together. So when we calculate the standard error is the standard deviation of your sample divided by the square root of n. So again, we can call that an estimate for the standard deviation of sample means. And I put this into list 1, my 6 numbers into list 1, found the mean, found the individual standard deviation, which was a sample so it's a statistic, and then I calculated my standard error. This is how I think X bars are going to vary from one to another if I use a sample size of 6. Now we want to calculate a 90% confidence interval. Now this is going to look much the same as what we did before. The only difference is, because we don't know the population standard deviation, we can't use our regular formula from Chapter 10. Chapter 10, we did this. That was our confidence interval formula to estimate for a mean. But now we can't use that because we don't know what the population standard deviation is. We're going to have to use an S here to estimate what this individual standard deviation is. But when we estimate this with an S, we have to change to something called a t-value. And so our formula for confidence interval is this formula. And so we're going to take X bar plus or minus, and now we're going to use a t-value times the standard error, which is just the standard deviation over the square root of n. But once we have to use a sample standard deviation to estimate the sigma, we have to switch to a t-distribution. Now, where do I find this value? And what is that degrees of freedom word, or that df that I have up there? So let's look in the back of the book. In the back of the book, we've used this table before. And this table has degrees of freedom along here. And our sample size was 6. So we are said to have n minus 1 degrees of freedom, so 5 degrees of freedom. And I wanted to find a 90% confidence interval. I'm going to double check. Yep, 90% confidence interval. So I can look down here. I see my confidence level down here. And I have to scroll up. And I also have to scroll over to 5 degrees of freedom. The degrees of freedom is always 1 less than the sample size. So the t-value that I'm going to use is 2.015. Now, it's calculated much the same way. I take what I got, plus or minus the t-star value for 5 degrees of freedom, times the standard deviation of the sample over the square root of n. And this number, when I take the standard deviation of the sample divided by the square root of n, is just called the standard error. And remember, again, it's just the idea of what the x bars, how the x bars sampling distribution would vary. And now I get this interval. I would interpret this the same way. I would say that 90% of calculated intervals will contain the actual population mean. So we're trying to find this person's phosphate level, the mean phosphate level. We're trying to get an interval estimate for this number. And 90% of the time when I crank out this type of a calculation, this interval will actually contain this true population mean in there somewhere. But unfortunately, 10% of the time it's going to miss. Okay, so we can see the confidence interval is basically calculated the same way. It's just we have to use sample data, sample standard deviation here, and that causes us to have to use a t-star value rather than a z-star value. Now, we are going to do hypothesis tests next, and our test statistic is going to look much the same as what a z-star value was, or a z-value. A z-value, when we're doing a hypothesis test, remember, was what you got minus what you're assuming divided by standard deviation over the square root of n. Well, because we're not in our hypothesis test on the next page, we're not going to know what the population standard deviation was. We can't use this z value. That was our old test statistic in Chapter 10. Now, this is unknown to us, so we'll use our sample standard deviation to estimate this sigma, and that means we'll be finding a t statistic rather than a z statistic. So let's turn the page. So my example here, I have, it doesn't matter what these measurements come from, but I have a series of measurements here that happen to be from some auto parts. And the first thing I'm going to do, and I have 16 measurements, so it's not a huge sample size, I graphed a histogram just to see if I have some skewness and outliers. Now, there's a little bit of skewness off to the right, but it's not terribly bad, and this test actually is pretty reasonable even if I have relatively small sample sizes. As long as I don't have extreme outliers and strong skewness, this test for doing hypothesis testing and confidence intervals is actually quite accurate. So secondly, I want to find out, we can see up here, I want to find, is there evidence that the mean dimension is not 224 millimeters? So we're going to do a hypothesis test. Now, there are some assumptions that we do want. We want these to be coming from a simple random sample. We would like our distribution to be approximately normal. Now, my graph, again, does not show total normality, but I only have 16 different numbers, so this doesn't look too terribly bad. And remember, you can actually change the interval over which you graph these and make these bars be different widths, and you can actually change the shape of the curve a little bit, so it's not too awfully bad as far as being approximately normal. Then I found what the mean and sample standard deviation is of all those individual 16 numbers by entering all my data into list 1 and getting the x-bar and the standard deviation. So now on a hypothesis test, remember we always go through and write our hypotheses down first. And because I'm trying to find out whether I have the dimension equaling 224 or not, I'm going to have a two-tailed test. Now, the next thing we do is we're going to have to calculate our test statistic. And let me draw a little graph here. We are assuming that the mean is 224. Now, we actually got 224.0019. We got something up here. But remember, on a two-tailed test, this value, and symmetrically located on the other side, this value, so the number that's 0.0019 higher or 0.0019 lower than 225 should be just as likely. So I need to find this test statistic for this value, and then I need to find the corresponding p-value. So I know here's the x-bar that I got, and I'm going to have 2 times that because I want both ends. And I need to convert it into a test statistic. Now, just because I don't know the population standard deviation, I'm going to use this S to find my test statistic. What I got minus what I'm assuming, and then the sample standard deviation over the square root of n. This whole thing, remember, is called the standard error. I have 16 pieces of data, therefore I'm said to have 15 degrees of freedom, and I need to find the corresponding p-value. Now, when I calculate this test statistic, I actually get 0.123. I'll show you how to use your calculator in a second to determine this, but if we use the back of the book, we actually can't find this probability. Okay, so I go here, and I look at my table for 15 degrees of freedom. And I'm looking for a test. These are the test statistics in here. The smallest test statistic I have is a 0.691. And that corresponds with an upper tail of 0.25. So I know my test statistic is actually over to the left of this, and the area that is going to be in this blue region for the number that's 0.123 is actually going to have an area bigger than 0.25. So I can't actually find my p-value for using this table. All I would be able to say is that my p-value would have to be larger than 50%. So from the table, I would know that the probability of t with 15 degrees of freedom, using again the table in the back of the book, this I would know has to be bigger than 0.25. And then I'm doubling it, so I would know that this probability would have to be at least 50%. So although I can't find the p-value using the table in the back of the book, I can find out that the p-value would be something bigger than 50%. And I don't care what significance level you use, you would never say that a p-value of more than 50% is something that causes you to reject the null. Because remember what we're doing. The p-value is saying if this mean is true, the likelihood of getting something like this or more extreme or symmetrically located on the other side or more extreme, that happens over 50% of the time. So we would say there is no evidence to show that the mean dimension is different from 224. That's totally normal for a distribution centered at 224 millimeters. Now, how did I get this value? Turn to my calculator on, went to second in distribution, and went to T-CDF. And the T-CDF, I put in, just like a normal CDF, I put in the 0.123, my test statistic, and then I want this tail. So I know that this value corresponds with 0.123 as a t-value, and I want to go up higher. And so I just put in a big value, much the same we do with a z-value. Now, the only thing differently is you do have to put in a comma and put what your degrees of freedom is. Now, that's the area of that upper tail. Because it's a two-tailed test, I have to multiply that by 2, and that gives me this value that I wrote down here. And I think that will be all for video 1.